Prescript declaration, open inside the quiet gap between China's electricity build-out pace and America's policy reaction cycle, where the mismatch is already measurable before it becomes political. Build a cause and effect chain where energy infrastructure speed sets industrial capacity, and industrial capacity then reshapes geopolitical leverage. The real competition is not clean energy adoption, but the difference in execution velocity between state-directed grid expansion and market-mediated permitting systems. Mood applied, cold and methodical, restrained tone, evidence-led pacing, minimal emotional signaling. Part 1. In 2023 alone, China added more solar capacity than the United States has ever built in its entire history. That number sounds exaggerated until you check it against the International Energy Agency's deployment tables. It holds. And it's not even the most important part, because capacity numbers are static. What matters is slope. You can feel the slope when you stop treating energy as a climate story and start treating it as a logistics system. Steel, copper, transformers, high voltage lines, permitting cycles that move in months instead of years. China is compressing those cycles in a way that doesn't look dramatic on the surface, but compounds aggressively underneath. And the United States reacts inside a different time system entirely. Not slower in intent, slower in structure. The Inflation Reduction Act of 2022 injected roughly $369 billion into clean energy incentives. That's not trivial. But incentives still have to pass through land rights, local opposition, grid interconnection queues, and litigation risk. Each layer acts like a brake pad, not a total stop, just enough friction to stretch deployment timelines into something that feels almost geological compared to China's construction cadence. Here's the part that rarely gets said clearly. China doesn't approve energy infrastructure in the same way. It assigns it. Provincial governments are evaluated on capacity additions, grid stability, and industrial output. That changes the psychology of decision-making. It turns delays into career risk. So when we talk about solar farms, wind corridors, ultra-high voltage transmission lines, we're not just comparing investment totals. We're comparing what happens after the investment is announced. In China, announcement and construction often overlap. In the US, they separate sharply. And that separation matters more than most models admit. Take ultra-high voltage transmission lines. China has built tens of thousands of kilometers of these lines in the last decade, connecting interior renewable zones to coastal demand centers. The US has struggled to build comparable long-distance transmission at scale, despite repeated federal prioritization. Not because the engineering is harder, it isn't. The constraint is coordination across fragmented jurisdictions, each with veto power. Different systems, different bottlenecks. Now, there's a common counter-argument that deserves attention. Markets allocate capital more efficiently, and that efficiency eventually outperforms state-directed systems. Historically, there's truth in that. Over long horizons, decentralized innovation tends to produce unexpected breakthroughs. But that argument assumes time is neutral. Energy transition isn't neutral in time. It compounds. Early grid dominance creates manufacturing clustering. Manufacturing clustering reduces costs. Reduced costs accelerate further deployment. It's a feedback loop that rewards whoever scales first, not necessarily whoever innovates best. And China understood that feedback loop early enough to design around it. The US, by contrast, optimized for price signals and private risk distribution, which works well in stable infrastructure eras. Less so in build-out races, where the constraint is physical volume, not capital availability. There's also something more subtle happening in supply chains. China didn't just expand solar panel manufacturing. It integrated upstream into polysilicon refining, wafer production, and inverter systems at scale. That vertical integration reduces exposure to global bottlenecks. It also means deployment can continue even when external trade conditions tighten. So when policymakers in Washington talk about catching up, they're often referring to installation targets, gigawatts per year, emissions curves. But underneath that is a harder question. Who controls the industrial stack that makes those gigawatts physically possible? Because once that stack consolidates in one geography, catching up stops being a policy problem and becomes a manufacturing one. And manufacturing has its own inertia. There's a moment in every industrial race where the conversation quietly shifts away from money and starts orbiting something more stubborn: coordination density. Not a phrase you hear often in policy circles, but it's the difference between drawing a plan and physically realizing it across thousands of sites that all have their own constraints, weather patterns, labor markets, and grid connections. China's clean energy expansion sits inside a system that treats coordination as a solvable engineering problem. In the United States, it often behaves like an accumulated negotiation. That difference shows up most clearly in transmission. You can generate all the solar you want in West Texas, but if you can't move it efficiently to where demand actually sits, you don't have energy. You have stranded capacity. The US has watched this problem grow in real time. The PJM interconnection queue alone has ballooned to thousands of gigawatts of proposed projects waiting years for approval. Some estimates from Lawrence Berkeley National Laboratory show average wait times stretching beyond 5 years in certain regions. At that point, pipeline starts to mean something closer to storage of frustration. China doesn't avoid these issues because it's immune to them. It avoids them because it changes the decision hierarchy. Local grid companies, provincial planners, and state-owned enterprises are aligned under performance metrics that reward completion, not deliberation. That doesn't eliminate inefficiency, it compresses it. A useful comparison is the development of ultra-high voltage, UHV, transmission corridors across China's interior. These are not marginal upgrades. They are backbone infrastructure projects moving gigawatts over distances that in other countries would require multiple competing regulators to approve separately. China's State Grid Corporation effectively treats these lines as national arteries. In the US, similar projects often become multi-year legal and environmental negotiations between states, utilities, and federal agencies. Now, the instinctive rebuttal is to say, yes, but at what cost? And that question is not trivial. Centralized acceleration can misallocate capital. It can overbuild capacity in regions that don't immediately need it. It can create redundancy that looks inefficient on paper. But the trade-off matters less when the objective function is expansion speed rather than perfect allocation. And this is where the conversation usually gets flattened in Western commentary. Efficiency is treated as the highest virtue. But in energy systems, timing can outperform efficiency. If you build a slightly suboptimal grid 5 years earlier than your competitor builds an optimal one, you often win anyway. Because industries don't wait for perfect infrastructure. They cluster around available infrastructure. Semiconductor fabs, battery plants, aluminum smelters, they all follow cheap, reliable electricity first and optimization second. There's another layer underneath this. Manufacturing ecosystems don't scale linearly, they scale in clusters. China's dominance in solar didn't come from isolated factories. It came from regional ecosystems where polysilicon plants sit near wafer slicing facilities, which sit near panel assembly, which sit near export logistics hubs. That proximity reduces friction at every stage: energy loss, transport cost, lead time, capital idle time. Each small reduction compounds. The US Inflation Reduction Act is attempting to recreate parts of that ecosystem, but it is doing so in a fragmented industrial geography that already exists. You don't start with a blank map. You start with legacy grids, legacy suppliers, and legacy zoning laws. That doesn't make replication impossible. It just slows the convergence curve. And while that convergence is happening, global demand is not waiting. Solar deployment worldwide is accelerating, particularly in emerging markets, where grid expansion is leapfrogging directly into renewables. Whoever can supply panels, inverters, and storage systems at scale during this window doesn't just capture market share, they define standards. There's a subtle geopolitical shift embedded here that doesn't get enough attention. Energy transition isn't only about decarbonization, it's about exportable infrastructure ecosystems. Whoever builds faster isn't just solving domestic demand, they are locking in external dependence through hardware compatibility, pricing dominance, and maintenance ecosystems. So when we talk about reaction speed between China and the US, we're not just talking about policy responsiveness. We're talking about who sets the tempo of a global industrial phase that will last decades. And that tempo, once set, is extremely difficult to slow down or reverse. At this point, there's a temptation to turn this into a clean winner-loser narrative. China builds faster, the US builds slower, end of story. But that framing collapses under the actual data once you start looking at grid reliability, capital efficiency, and the hidden costs of speed. Because China's expansion is not frictionless. It just hides friction differently. Curtailment is one example. In some northern provinces, wind and solar projects have historically been built faster than the grid's ability to absorb them. That leads to energy being produced but not fully used, essentially wasted generation because transmission or demand timing isn't aligned. State Grid Corporation of China has reduced curtailment rates over the last decade, but the pattern still appears in waves when build-out accelerates ahead of absorption capacity. So the system is not perfectly coordinated. It's aggressively corrected after mismatches appear. The US, by contrast, tries to prevent mismatch before it happens. Environmental review processes, multi-stakeholder grid planning, and litigation risk frameworks are all designed to minimize structural mistakes. But that caution produces its own distortion. Delay becomes the dominant form of risk control. And delay is not neutral. It reshapes investment behavior. Developers in the US increasingly price regulatory time into their models. A solar project isn't just capital expenditure plus operating return anymore. It's capital plus uncertainty premium. That premium changes what gets built, where it gets built, and whether it gets built at all. Meanwhile, China's renewable build-out is now interacting with something even more complicated: demand reconfiguration. Electric vehicle penetration, industrial electrification, and data center expansion are beginning to shift load curves in ways that weren't fully anticipated a decade ago. China added over 8 million EVs in 2023 alone, according to industry registrations. That changes not just electricity demand, but timing of demand, night charging, peak shaving, regional stress points. So the system is now chasing a moving target. And here's where the narrative gets uncomfortable for both sides. China's advantage in speed is real, but it is not purely structural genius. It is also the product of centralized risk tolerance that absorbs mistakes internally. Some projects are overbuilt. Some infrastructure arrives ahead of demand. Some capital is locked into assets that take years to fully justify themselves. The US advantage, often framed as discipline, is also not purely virtuous. It prevents large-scale misallocation, yes, but it also prevents large-scale acceleration. The same mechanism that stops bad projects also slows good ones. Two systems optimizing for different failure modes. There's a deeper point hiding underneath this that often gets missed in clean energy debates. Energy transitions are not just engineering problems. They are synchronization problems between institutions, capital, and physical infrastructure. And synchronization is harder than invention. Solar panels are not the constraint anymore. Neither are wind turbines or battery chemistry at a basic level. Even lithium supply, while volatile, is expanding faster than it was 5 years ago due to new processing capacity in South America and Australia. The constraint has moved upward into permitting systems, grid architecture, and institutional alignment. That's why comparing China and the US purely on installed gigawatts misses the real divergence. One system is optimized for throughput, the other is optimized for procedural correctness. Neither is universally superior. But in a world where energy demand is rising again, not falling, throughput starts to matter in a way that feels increasingly hard to ignore. There's also a strategic layer here that doesn't get enough attention in public discourse. Control over renewable manufacturing doesn't just mean export revenue, it means control over upgrade cycles. Whoever controls inverter standards, battery management systems, and panel replacement logistics effectively sets the rhythm at which other countries can modernize their grids. That's not dominance in the old military sense, it's dependency through maintenance schedules. And once that kind of dependency forms, it doesn't show up in headlines. It shows up in procurement contracts signed quietly over decades. So when people ask whether China is ahead in clean energy, the more precise question is, ahead in what dimension? Speed? Yes. Coordination? Often. Efficiency? Not always. Resilience? It depends on the metric and the shock scenario. And that ambiguity is exactly why this race is harder to read than it looks from the outside. There's a point in every long industrial shift where the numbers stop feeling like data and start behaving like momentum. You don't need to believe a narrative for it to matter. It just accumulates until policy, markets, and strategy are forced to move around it. Clean energy has reached that phase. China isn't racing the United States in the way sports analogies suggest. It's closer to something more structural, a compounding system where each year's capacity becomes next year's baseline constraint for everyone else. Once you see it that way, the debate about intention becomes less important than the shape of execution, and the shape is uneven. Take manufacturing again, because it's where the abstraction collapses into physical reality. China's dominance in solar panel production didn't just come from subsidies or scale alone. It came from controlling bottlenecks that sit far upstream: metallurgical-grade silicon refining, precision glass production, and high-efficiency cell assembly lines that require tightly coordinated supplier ecosystems. Once that stack is in place, it starts reinforcing itself. Suppliers move closer, talent pools specialize, shipping routes adjust, even financing becomes more localized because lenders understand the cycle better than outsiders. The US is trying to rebuild parts of that stack under the Inflation Reduction Act framework, and there is genuine movement. Battery plants in Georgia, solar assembly expansion in Texas, grid modernization funding spread across multiple federal programs. But the sequencing is different. It is retrofitting into an existing industrial map rather than designing a new one. That matters more than most policy discussions admit, because retrofits inherit friction. Now, I want to challenge the simplest version of the China is ahead argument, because it's incomplete in a way that actually matters for forecasting. China's system is extremely good at mobilization, but it is also sensitive to internal calibration errors, overcapacity cycles, local government debt exposure, and periodic mismatches between installed infrastructure and actual demand growth. The National Energy Administration has had to repeatedly adjust renewable curtailment policies and grid absorption targets to deal with exactly this tension. It's not instability in the collapse sense. It's instability in the calibration sense. The system occasionally overshoots and then corrects. The US system, meanwhile, produces fewer large-scale misallocations, but pays for that with chronic underbuild. An underbuild has a compounding cost of its own: deferred electrification, higher energy prices for new industrial entrants, and slower grid modernization timelines that push investment offshore. So the real divergence is not competence versus incompetence, it's error type. One system risks building too much too fast. The other risks not building enough for too long. And those two errors behave very differently in a world where electricity demand is structurally rising again because of data centers, AI infrastructure, EV fleets, and industrial reshoring. That last point is where the trajectory starts to matter more than the snapshot. If you assume global electricity demand growth accelerates through the 2030s, and most projections from the International Energy Agency and Bloomberg NEF lean that way under multiple scenarios, then the first mover in cheap, scalable, renewable heavy grids doesn't just gain domestic advantage, it shapes global cost curves. That's the part that tends to get underestimated. Energy systems don't just supply economies, they price them. And pricing power, once embedded in industrial inputs like electricity, cascades into everything from aluminum production to semiconductor fabrication to AI training clusters. So the question stops being who is ahead right now and becomes something more uncomfortable. Who is setting the default cost of the future? My read is this: China is currently setting the pace of physical deployment, especially in solar and grid expansion. The United States is setting a slower but still meaningful pace in innovation and capital structuring. Those two roles can coexist for a while, until global demand forces convergence or conflict over standards. But I don't think that balance holds indefinitely. Either the US compresses its deployment timeline significantly over the next decade, or it gradually cedes influence over the physical infrastructure layer of the energy transition. And that leads to the part I keep coming back to. If deployment speed continues to diverge, we don't just get different energy systems, we get different industrial realities, ones that are increasingly incompatible at the margins. No easy resolution there, just a narrowing set of options. If you've watched this far, it's probably worth asking yourself a simple question. Are we still in a transition phase, or are we already watching two separate systems harden into parallel versions of the same future? If you want, I can take the next one into how this feeds directly into AI infrastructure and data center power wars. That's where this gets sharper very quickly.